Hello, welcome again. We are solving GATE 2022 Aerospace Engineering paper. Question number 60 is a 10 kilonewton axial load is applied eccentrically on a rod of square cross section 1 centimeter into 1 centimeter as shown in the figure. The strains measured by two strain gauges attached to the top and bottom surfaces at a distance of 0.5 meter from tip are epsilon 1 is equal to 0.0016 and epsilon 2 is equal to 0.0004 respectively. The eccentricity in loading is E. E is dash mm. Okay, so this is the figure. This is here the strain is epsilon 1, here the strain is epsilon 2, 0.5 meter and 100 kilonewton, and this is E. This is 1 centimeter and 1 centimeter cross section area. Now it is given that the strain at top is zero point 0, epsilon 1 is 0.0016 and epsilon 2 is the strain at bottom is 0.004. So as we can see that the strain at 1 and 2 is due to two reasons. One is due to direct stress and one is due to bending. Bending because this 10 kiloton load is acting at an eccentricity E. So this bending will cause an extra strain in topmost part and extra tensile strain in topmost part and extra compressive strain in bottommost part. So the strain in the topmost part will be more and strain in the bottommost part will be less. Okay, but it will follow a linear variation because the bending stress is following a linear relationship from top to bottom, and it is 0 at neutral axis and maximum at top, maximum tensile at top and minimum or maximum compressive at bottom. Okay, and a uniform stress due to this 10 kilonewton direct load is also active. Okay, so average of these two will give the strain at neutral axis. Neutral axis. So because at neutral axis no bending stress is acting, only the direct stress is acting. So direct stress means will cause direct strain. So average of these two is uh, 0.1, 0.001. Okay, so that is the strain at the neutral axis. Okay, and the strain at the neutral axis is only due to the direct stress. So and the direct stress is direct load by area. Okay, so that is your 100 newton per mm square. So this is your 10 centimeter or 10 1 centimeter or 10 mm, converting into mm, and this is into newton. Okay, now this is the direct stress and this is the direct strain at neutral axis, and Young's modulus is 100 by 0.001, where 100 newton per 3 MP. Okay, now this direct strain is occurring uniformly throughout this section. Okay, so the strain at the top fiber is strain at the top fiber is this is the average strain at the neutral axis, and this is the this strain is also uh, acting at the top fiber. So bending strain will be total strain minus direct strain, that is your 0.006. Okay, so as the bending strain is 0.006, so the bending stress will be sigma by E, sorry, sigma by this strain, sorry, E into this strain. Okay, so the bending stress will be this strain into E. So using bending equation m by I sigma by y, so m is your 10 into 1000 into E, I is your 10 into 10 cube by 12, y is your 10 by 2, that is 5 mm. So putting the values we can get E as 1 mm. Okay, so answer is 1 mm. So eccentricity is your 1 mm. Next, for a thin wall die section, width of the two flanges as well as web height are same, that is 2b is equal to 20 mm. Thickness is 0.6 mm. The second moment of area about a horizontal axis passing through centroid is dash mm4. So this is 2b, this is 2b, this is 20 mm, this is 20 mm. Okay, so moment of inertia is for this flange is 20 into 0.6 cube by 12, and similarly for this also, so we can multiply by 2. So as it is splitting section, the center lies at between in between. So using parallel axis theorem, this is the moment of inertia about their centroidal axis, about this and about this. Now we have to shift the moment of inertia, find out the moment of inertia about the centroid. Okay, so we have to use parallel axis theorem. So here the distance is uh, 10 plus 0.3. So distance is using parallel axis theorem, the distance between the center of this axis and center of this axis is 10.3 square. Okay, into area of this is 20 into 0.6, and as there are two places, we are taking this for this also, so we will multiply 2. Okay, and moment of inertia of this part is your 20 into sorry 0.6 into 20 cube, okay, by 12. So solving this we get 2946.88 mm4. Okay, next, a damper with damping coefficient C is attached to a mass of 5 kg and spring of stiffness 5 km per meter, as shown in figure. The system undergoes underdamped oscillation. If the ratio of third amplitude to the fourth amplitude of oscillation is 1.5, the value of C is dash Newton second per meter, rounded up to nearest figure. So this is your this is a spring of stiffness 5 km per meter. This is damping, and this is 5. So x3 by x4 is your E 2 pi xi divided by root 1 minus xi square. Okay, so that is the amplitude ratio. So x3 by x4, and xi is your damping ratio. So x3 by x4 is given as 1.5. So that is 1.5, and that is equal to 2 pi xi 1 minus xi square. Or taking ln both sides, it will be 0.4054, and this will be 2 pi xi 1 minus xi square. So taking square, so that will be 0.1644 1 minus xi square, 4 pi square xi square. Okay, solving this we have xi is equal to 0.004. So xi is your damping ratio, and damping ratio is given by C by Cc. C is your damping coefficient, and Cc is your critical damping coefficient. Critical damping coefficient is 2 root Kn. Okay, so putting the value here, we can get as K is 5 kg and sorry, K is 5 into 1000 kilonewton into converting kilonewton into Newton, that is 5000, and M is 5. Okay, so putting the value here, so we get C as 20.36. So damping coefficient is 20.36 Newton second per meter. Okay.